Hey everyone, welcome to another deep dive. You ready to get quantum?
I am.
Let's do it.
Okay, so today we're diving into quantum entanglement. And we're going to be using a PhD thesis on multipartite entanglement.
Okay.
And looking at chapters 1, 2, and 3. And these chapters cover like the history of quantum mechanics, a basic intro to entanglement, and then bipartite entanglement.
Right.
So we're going to go from like the very basics all the way to some pretty complicated stuff.
Sounds good.
But entanglement is like the backbone of, quantum computing.
Yeah.
Quantum information science.
Yeah.
It's pretty much the reason why everyone's so excited about quantum stuff these days.
It's really amazing that something that was once considered just like a theoretical oddity, is now like right at the center of this huge emerging field.
Yeah.
So
It's pretty wild.
yeah.
So to start off, this whole idea of entanglement kind of has its roots in this problem that physicists were having back in the 1800s. And it all started with how much energy a hot object gives off.
Oh wow. So like physicists like Gustav Kirchhoff were really puzzled by this.
So Kirchhoff, this is blackbody radiation.
Yeah.
Right? Yeah.
Yeah.
His work on blackbody radiation was really crucial because he kind of set the stage for this revolution
Yeah.
in physics. He showed that a black body, which is this perfect absorber and emitter of energy, emits energy at a rate that just depends on its temperature
Yeah.
and the frequency of the energy.
Right.
But the formula for this rate was a complete mystery,
Yeah.
and he challenged the physics world to find it.
Yeah, like what is going on here? And then Max Planck came along in 1900 and kind of dropped a bomb on classical physics.
The bomb, how's that?
So he figured out the formula. But to do so, he had to assume that energy didn't come in the smooth, continuous flow that everyone thought, but it came in these tiny little discrete packets called quanta.
Wow. Okay, so that was a huge deal.
Yeah,
that was really the birth of quantum theory. This idea that energy exists in these fundamental units.
Yeah.
And it was a radical idea at the time.
I bet people were not happy.
Yeah, as you can imagine, a lot of physicists were very resistant to this idea. They'd built their whole careers on classical physics.
Yeah.
But then Einstein, Einstein saw the potential in Planck's work.
Right. Einstein loved this.
Yeah, he used it to explain the photoelectric effect, which is where light shining on a metal can actually knock electrons loose.
Yeah, so light is knocking stuff loose.
Yeah.
How does that even make sense?
Well, Einstein explained it by saying that light itself is quantized. It's made up of these little packets of energy called photons.
Okay, so light is both a wave and a particle.
Yeah, wave-particle duality.
Yeah, that's right.
It's mind-blowing.
Yeah, it's one of the core mysteries of quantum mechanics. But it was a huge success for the quantum theory.
Yeah, for sure.
And then Bohr took this idea of quantization and applied it to the atom. He proposed that electrons orbit the nucleus in these specific energy levels.
Okay.
And these early successes of the quantum theory, like Einstein explaining the specific heat of solids, started to bring quantum theory into the mainstream. Right. So we're starting to see these little pieces of the puzzle come together.
Yeah. It's starting to make more sense.
But it wasn't a unified theory yet, right?
Right. It was still what they call the old quantum theory. It worked for some things, but it wasn't a complete or consistent picture of the world.
So how do we get from this kind of hodgepodge of ideas to a more coherent framework?
Well, a major step was Bohr's correspondence principle,
Okay.
which basically stated that for large systems, quantum mechanics have to agree with classical physics.
Right.
Like the results should match up.
Like it can't just be totally different.
Yeah, exactly.
Okay.
So that was a really important bridge between the quantum world and the macroscopic world that we see.
Right.
And this bridge, along with an increasing focus on the probabilistic nature of quantum events, really set the stage for a new era in quantum mechanics.
Okay, so things are getting interesting now because now we have two different quantum theories popping up at roughly the same time.
So what are these two theories?
We have Heisenberg's matrix mechanics, which is all about this discrete energy jumps. And then we have Schrodinger's wave mechanics, which is building on that wave-particle duality we were talking about.
Okay.
So it's like two totally different ways of looking at the quantum world.
It must have been a very confusing time for physicists.
I can't even imagine trying to wrap your head around all of that.
So were these theories ultimately right or wrong?
Well, it turned out that they were actually mathematically equivalent.
Oh, wow. Okay.
So they were just two different ways of describing the same underlying reality. But the big question was how to interpret them. And that's where the Copenhagen interpretation came in.
Okay, so this is like the the dominant.
Yeah, this is kind of the standard way we understand quantum mechanics today. And it basically says that, we can only predict the probabilities of quantum events happening, not the actual outcomes themselves.
Okay, so it's all about probability.
Yeah, it's like the universe is playing dice.
Which is something that Einstein famously objected to.
Oh.
Right. God does not play dice. It's one of his most famous quotes.
He was not a fan of this idea.
No, he really wanted to believe that there was some underlying determinism to the universe, that things weren't just random.
I guess it's hard to let go of that classical way of thinking.
Yeah.
Where everything is predictable. Okay, so we've kind of laid the groundwork here. The history, the key players, the weirdness. But to really dive deeper into entanglement, we need to talk about the math.
Okay.
And the thesis introduces this concept of Hilbert space, which honestly sounds a bit intimidating.
Yeah, it sounds a little scary. But is it really that bad?
Not really. It's just a fancy way of talking about the mathematical space where quantum states live.
So it's like a canvas where quantum states get to express themselves.
Yeah, that's a good way to put it. And the thesis uses the example of a qubit, which is like the quantum version of a bit.
Right. So instead of just being a 0 or a 1, it can be in this fuzzy state called a superposition.
Right. It can be both 0 and 1 at the same time.
Yeah. And that's where things start to get really weird.
And the math that describes this is called Dirac notation or bracket notation. And it's a really elegant way to express things like pure quantum states, which are represented as unit vectors in this Hilbert space.
So we're using vectors and matrices to describe things happening at the subatomic level.
Pretty much.
It's like we're doing surgery on reality itself.
Yeah, it's pretty wild. And then on top of that, we have operators.
Okay, so what are operators?
They're mathematical operations that act on these quantum states.
So they're like the surgical tools.
Yeah, exactly. And the thesis specifically mentions unitary operators, which are transformations that preserve the inner product of the Hilbert space.
So they make sure that our quantum state stays well behaved during all these mathematical manipulations.
And then there are Hermitian operators, which correspond to physical observables.
Okay, so things we can actually measure.
Yeah, things like energy or momentum.
So it's not all just probabilities and uncertainty. We can actually measure stuff in this quantum world.
A measurement is a big deal in quantum mechanics.
Right.
And when we measure something, it forces the quantum state to collapse.
Collapse. What does that mean?
So all those possibilities suddenly shrink down to one reality.
Just because we looked at it?
Yeah, it's like the universe is choosing from a menu of possibilities, and our observation forces it to make a choice.
That's a really mind-boggling concept.
It is. And it gets even more complex because when you combine multiple quantum systems, the dimensions of this Hilbert space grows exponentially.
Okay, so the canvas gets bigger and bigger, and it allows for these increasingly complex interactions.
And that's where entanglement really comes into play.
All right, so let's finally talk about entanglement, this spooky action at a distance that Einstein was so skeptical of.
Yeah, what is this entanglement thing all about?
Well, the thesis defines entanglement as this: uniquely quantum phenomenon, where two or more particles become correlated in a way that just can't be explained by classical physics.
Okay, so they're linked even when they're separated by huge distances. All right, so to understand entanglement, we need to talk about the difference between separable and entangled states.
Okay, so separable states, those are like classical correlations.
Yeah, like if you have two coins and you flip them, knowing that one landed on heads doesn't tell you anything about the other one.
Yeah, they're independent. But entangled states are different.
Yeah, they're like magically linked.
Yeah, it's like those two coins. But instead of being independent, they're linked so that they always land on opposite sides.
Okay, so if you know one is heads, you instantly know the other one is tails.
Yeah, even if they're miles apart.
That's so weird.
Yeah, it's one of the most bizarre and counterintuitive aspects of quantum mechanics.
Okay, so how does the thesis tackle this mathematically?
Well, it delves into the Bell states, which are like the quintessential examples of entangled states. They're maximally entangled states of two qubits.
So we're talking about pure states here.
Right.
Not mixed states.
Yes.
Just to remind our listeners, a pure state is like a single, well-defined quantum state. And a mixed state is like a combination of different pure states.
So a pure state is like a pure ingredient.
Okay.
And a mixed state is like a recipe.
Yes, exactly. So these Bell states are like the purest form of entanglement you can get with two qubits. Okay, so how do we even quantify entanglement?
Well, the thesis introduces this tool called Schmidt decomposition.
Okay, Schmidt Decomposition, what is that?
It's a way to analyze bipartite pure states.
So states with two entangled systems.
Yes.
Okay.
Yeah, basically, any pure state of two systems can be expressed as a sum of products of states from each system.
Okay.
And each of these products has a coefficient called a Schmidt coefficient.
So it's like breaking down the entanglement into its basic building blocks.
Yeah, and seeing how much each block contributes to the overall entangledness.
Okay.
And the number of these Schmidt coefficients that are greater than 0 gives you something called the Schmidt rank.
Okay, Schmidt rank. What's that tell us?
Well, the thesis explains that the Schmidt rank is directly related to how entangled the state is.
So a higher Schmidt rank means more entanglement.
Exactly.
Okay, so there are degrees of entanglement.
There are Schmidt rank of 1 means the state is separable. So no entanglement,
Yeah.
but anything higher. And you've got entanglement on your hands.
Okay, cool. So we can actually quantify this spooky action at a distance.
They can.
But this is still all very theoretical. Like, how do we know this isn't just some mathematical quirk?
Right. How do we know it's real? Well, that's where the EPR paradox comes in.
Okay, EPR paradox.
Yeah, it's named after Einstein, Podolsky, and Rosen. And it was a thought experiment designed to challenge the completeness of quantum mechanics.
So they were basically saying, quantum mechanics can't be the whole story.
Yeah, they thought there must be something missing. They argued that if you could predict the outcome of a measurement on one entangled particle by measuring the other particle, then those properties must have existed beforehand, independent of measurement.
Okay.
They called this local realism, this idea that physical properties have definite values, even before we measure them.
But that's not how quantum mechanics sees things.
No, according to quantum mechanics, these properties don't have definite values until they're measured.
And the act of measurement affects the system.
Yeah, it's like the universe is making a choice when we observe it.
Okay, so how do we settle this debate?
Well, that's where John Bell comes in, and his famous Bell inequalities,
Okay.
Bell's theorem, provided a way to experimentally test the predictions of local realism against the predictions of quantum mechanics.
So it's like setting up a duel.
Yeah, a duel between two competing views of reality.
And who won?
Well, the experimental results were in.
Yeah.
And they showed that quantum mechanics was right.
So entanglement is real.
It is. This spooky action at a distance is a real phenomenon.
That's crazy.
Yeah, it really challenges our intuition about how the world works. But the thesis also mentions this thing called the no communication theorem.
Okay, the no communication theorem.
Yeah, so does that mean we can use entanglement to send messages faster than the speed of light?
That would be amazing.
It would, but unfortunately, that's not how it works.
That's okay, so no breaking the cosmic speed limit.
No.
Yeah.
But even though we can't use entanglement to send information faster than light, it still has a lot of potential applications.
Yeah, like what?
Well, in quantum information science, for example,
Okay.
entanglement is seen as a valuable resource. It can be used to do things that are just impossible with classical physics.
So like quantum teleportation.
Yes.
Super dense coding.
That's right.
Entanglement swapping.
Exactly.
Okay, hold on. Things are getting even weirder.
They are.
Yeah.
But before we get into all of that, the thesis first focuses on bipartite entanglement.
Okay, so we need to understand entanglement between two systems before we can move on to the more complicated stuff.
Exactly. It's like laying the foundation.
Okay, so let's dive into bipartite entanglement and see what other surprises this quantum world has in store for us.
Let's do it.
All right, so we're back and ready to explore bipartite entanglement.
Okay.
So last time we kind of established that entanglement is real, and now we're going to focus on entanglement between two systems.
Right, the two-player version
Yeah, exactly.
of this quantum game.
So imagine like you and I each have one of these entangled particles, but we're miles apart.
Oh, yeah.
What can we actually do with them?
That's where this idea of LOCC comes in.
LOCC.
Yeah, local operations and classical communication.
Okay, so that's like the rule book for this quantum game.
It is. It sets the boundaries for how we can manipulate these entangled states when we're separated.
Okay.
So we can only perform operations on our own particle.
Right.
We can apply a unitary operator
Right.
or make a measurement. And we can talk to each other on the phone. That's the classical communication part.
Right.
But we can't directly exchange quantum information.
Okay, so it's like we have these powerful quantum tools, but we're playing this long-distance game with some serious restrictions.
Yeah, a great analogy. And the thesis explains that within these LOCC constraints, we can actually classify different types of bipartite pure states.
Okay, so how do we do that?
Well, this is where this concept of majorization comes in.
Majorization. All right, hit me with it.
So remember those Schmidt coefficients?
Well, yeah.
Those numbers that tell us how much each piece contributes to the overall entanglement. Well, majorization is a way to compare two sets of Schmidt coefficients.
So we're comparing like the entanglement recipes
Yeah.
of two different states, seeing which one has like a stronger flavor of entanglement.
Precisely. And if you arrange these Schmidt coefficients in decreasing order for two different states, you can determine if one state can be transformed into the other using LOCC, just by comparing those lists.
Okay.
So it creates this hierarchy of entanglement based on how versatile a state is.
So it's not just if a state is entangled, but how entangled it is relative to other states.
Exactly.
Right.
And the thesis actually identifies a king of bipartite entanglement.
A king. What do you mean?
So there's this state that can be transformed into any other bipartite pure state using LOCC.
Oh, wow.
It has the most evenly distributed set of Schmidt coefficients, making it incredibly versatile.
So it's like the master chef of entanglement.
Yeah, I can whip up any other entangled state using LOCC.
That's pretty cool. So where do the other states fall in this hierarchy?
Well, you can create this whole family tree of entangled states based on their majorization relationships.
Oh, wow.
You can trace the lineage and see which states could be transformed into others using LOCC.
So it's like a genealogy of entanglement.
That's a great way to put it. But then the thesis throws in this curveball,
Okay.
SLOCC.
It's LOCC.
Yeah, stochastic, local operations, and classical communication.
Okay, so it's like LOCC, but with a twist.
It
It is the twist.
Well, instead of requiring that our transformations succeed with 100% certainty,
Hmm.
SLOCC allows for some probability of failure.
So we're adding a little bit of chance to the game.
Yeah,
Okay.
we might not always get the exact state we want,
Mm-hmm.
but we have more options to play with.
Okay. I like that.
And the thesis points out that with SLOCC, you can actually transform any pure bipartite entangled state into any other,
Okay.
although the probability of success will vary.
So there's like this underlying unity to all these bipartite entangled states.
Yeah, they're all part of the same family,
Yeah.
just with different quirks and personality.
I like that. Okay, so we've been talking about pure states this whole time, but the real world is messy.
Right.
What happens when we deal with mixed states?
That's a great question.
Those recipes of quantum states.
Yeah, things get a lot trickier.
I bet.
So first, just to remind everyone, a product state is when two systems are completely independent,
Right.
flipping two unrelated coins. And a separable mixed state is just a mix of those product states, like
Yeah.
having a bag of coins, some linked and some independent.
Okay.
And if it's not separable, then it's entangled.
But how do we tell the difference?
Well, that's where the PPT criterion comes in.
PPT criteria.
Yeah, it stands for positive partial transpose.
Okay, what is that?
It's basically a test
Mhm.
to see if a mixed state is entangled or not.
Okay, how does it work?
Well, it involves this mathematical operation called a partial transpose.
Partial transpose. So
Yeah.
we're not flipping the entire matrix, just part of it.
Yeah, it's a bit delicate.
Yeah.
But the cool thing is, if the partial transpose of the density matrix is positive semi-definite, meaning all its eigenvalues are non-negative,
Okay.
then the state is separable.
So no entanglement.
No entanglement. It's like a green light. You're good to go.
But if those eigenvalues go negative, then bam, entanglement.
Exactly. You found it.
And this PPT criterion, it's actually complete for some low-dimensional systems.
It is.
Meaning it can detect all entangled states in those cases.
That's right.
But unfortunately, it's not foolproof for higher dimensions.
No.
So it's a great tool, but it's not a universal entanglement detector. Okay, so what else do we have?
Well, the thesis also talks about these things called positive but not completely positive operators.
Positive, but not completely positive.
It's a mouthful.
Yeah.
But basically, these are special functions that act on our quantum states
Okay.
and a positive operator.
Yeah.
Apps positive semi-definite matrices.
Okay.
Two positive semi-definite matrices.
Okay, so it's like a well-behaved guest. It doesn't cause any trouble. But a completely positive operator is even better. It is. It stays positive, even when you combine the system with another system. So it's like a super positive guest that
right.
gets along with everyone.
Okay.
And the key insight here is that these positive, but not completely positive operators can act like entanglement detectors.
Okay, so how does that work?
Well, if you apply one of these operators to a separable state and the result stays positive, semi-definite, then you know it's separable.
Okay.
But if it dips into the negative, you've found entanglement.
So they can, like, smell the entanglement?
Yeah, that's a good way to put it.
Okay.
And then they're entanglement witnesses.
Entanglement witnesses.
Yeah, they're basically observables that are designed to flag entanglement. Their expectation value is always non-negative for separable states, but it can go negative for entangled states.
So they light up when they encounter entanglement.
Exactly. And the great thing about entanglement witnesses is that they can be directly measured in experiments. Okay, so we don't need to fully characterize the state to know that it's entangled.
Right. It's a shortcut to proving entanglement.
That's handy.
Yeah.
But not all witnesses are created equal, right?
No, some are more sensitive to entanglement than others.
So it's like having different strengths of magnifying glasses.
Yeah, you want the one that can spot even the faintest traces of entanglement.
And the thesis talks about optimal entanglement witnesses.
Right.
So these are like the best of the best.
They are.
At detecting entanglement.
But finding these optimal witnesses, it's still an active area of research.
Okay.
It's a tough problem.
So we've got all these different ways to detect entanglement in mixed states.
Yeah.
The PPT criterion, positive but not completely positive operators. Entanglement witnesses. Are there any other tests out there?
There are. The thesis mentions a few others.
Like what?
Like the CC&R criterion.
TCNR.
Yeah, it stands for computable cross norm or realignment criteria. It's a bit of a mouthful. But basically, it involves rearranging the elements of the density matrix and checking if the sum of its singular values exceeds a certain threshold.
Okay.
And if it does, you've got entanglement.
We're shuffling the pieces of the density matrix puzzle
Yeah.
and seeing if they fit together in a way that screams entanglement.
Exactly.
Okay, and what about the range criterion?
So the range criterion focuses on the range of the density matrix, which is the set of all possible output states.
Okay.
And for a separable state, this range can be spanned by a set of product vectors. But if you can't find such a set, then you know you've got entanglement.
Okay, so we have all these clever ways to detect entanglement,
Yeah.
but once we've confirmed it's there, what can we actually do with it?
Well, that's where things get really interesting.
Okay.
The thesis talks about entanglement distillation.
Entanglement distillation.
Yeah, it's like you're taking raw entanglement
Right?
and refining it into a more potent form.
Okay, so imagine we have a bunch of copies of a mixed entangled state,
Right.
but the entanglement is a bit impure.
Yeah, it's like we have boxes filled with these entangled particles. But the entanglement is a bit diluted,
Okay.
and we want to perform some fancy quantum protocol.
Right.
That requires a pure entangled state, like those pristine Bell states we talked about.
Right.
Well, entanglement distillation is the process of using LOCC to transform those many copies of a mixed state into fewer copies of a pure entangled state.
So it's like taking a bunch of diluted juice and concentrating it into a smaller amount of pure flavorful juice.
Exactly.
Okay, I like that. And the thesis gives an example of how to distill entanglement from Werner states.
Right.
So Werner states are kind of like the lab rats
You could say that.
of entanglement distillation. So the thesis describes this protocol where you start with 2 copies of a Werner state and you use local operations and measurements and classical communication.
To get a pure entangled state.
Okay.
Something closer to that ideal Bell state.
So it's a recipe for squeezing out more entanglement
Yeah.
from the state you have. Okay, cool.
But then the thesis throws in another curveball.
Another one. What is it this time?
Sound entanglement.
Sound entanglement.
Yeah.
What's that?
It's one of the most fascinating puzzles. In quantum information theory,
Okay.
it refers to entangled mixed states. That can't be distilled into pure entanglement using LOCC.
Wait, so it's entangled, but we can't use it to create pure entanglement.
That's right.
What's the point of that?
What really challenges our understanding of entanglement and the limits of LOCC. It suggests that there are different flavors of entanglement, some more readily accessible than others.
Okay, my mind is officially blown. We've explored how to classify bipartite entanglement, learned about all these different tools for depicting it in mixed states, even touched on this idea of distilling it into a purer form. But now we have this new mystery, bound entanglement. Entanglement that's trapped. Inaccessible.
It's like the universe is teasing us.
I know, with possibilities. But what happens when we go beyond 2 entangled systems?
That's a great question.
What about those multipartite entangled states with 3, 4, maybe even hundreds of entangled particles?
That's where things get really wild.
Okay, I'm ready. Let's do it. All right, we're back and ready for the big leagues multipartite entanglement.
Multipartite entanglement.
So we've explored entanglement between two systems, but now we're talking 3, 4, maybe even hundreds of entangled particles.
Yeah, it's a whole new level of complexity.
I can only imagine. Bipartite entanglement was already pretty mind-blowing. So how do we even begin to make sense of this?
Well, the thesis starts by introducing this concept of K-separability.
K-separability.
Yeah, so with bipartite entanglement, we had this simple distinction. Separable or entangled.
Right.
But with multiple systems, you can have different degrees of separability.
Okay, so it's not black and white anymore. There are shades of entanglement.
Exactly.
Okay, so can you give me an example?
So imagine we have 3 particles. They could all be entangled together, forming a genuinely tripartite entangled state.
Okay.
But you could also have a situation where 2 of the particles are entangled, and the third one is off doing its own thing.
Right.
Completely independent. Or all 3 particles could be independent. Like 3 soloists with no harmony.
Okay, so K-separability tells us how many independent groups of particles we have.
Exactly.
Okay.
And as you add more particles, the number of ways you can group them explodes.
Combinatorial explosion.
It really does.
Okay, so this is getting complicated quickly.
That is.
So does the thesis give any specific examples of these multipartite entangled states?
It does. It introduces the GHZ states.
GHZ state.
Yeah, named after Greenberger, Horn, and Zeilinger.
Okay.
And these states are prime examples of genuinely multipartite entangled states,
Yeah.
where all the particles are linked together.
Okay, so if we have 3 particles in a GHZ state, they're all in it together.
Yeah.
No lone wolf.
No lone wolves.
Okay.
So for 3 qubits, the
Yeah.
GHZ state is a superposition of all 3 qubits being 0 and all 3 being 1. They're either all heads or all tails together.
So it's like those 3 particles are perfectly synchronized,
Yeah.
even though they could be miles apart.
It's like they're acting as one.
Okay, that's pretty wild.
It is.
And the thesis also mentions the W state, right?
The W state,
Yeah.
yes. Another interesting example of tripartite entanglement.
So what's different about the W state?
So for 3 qubits, it's a superposition of states where exactly 1 qubit is 1 and the other 2 are 0.
Okay, so instead of all 3 particles being synchronized, like in the GHZ state, the W state has just one of them flipped in each possible combination.
Exactly.
So each particle takes turns being the odd one out.
Yeah, but they're still linked together in this quantum way. And the thesis emphasizes that the W state and the GHZ state are fundamentally different types of entanglement.
Okay.
You can't transform one into the other using SLOCC, even though they both involve 3 entangled particles.
So even with just 3 particles, we already have this diversity of entanglement.
We do.
It's crazy.
And for systems with more than 3 particles. Classifying these multipartite entangled states becomes incredibly complex.
I can only imagine.
There are infinitely many families of entangled states.
Infinitely many. Okay, my brain is officially melting.
It's a lot to take in.
So how do we even begin to explore this?
Well, first, we need to be able to detect multipartite entanglement. And some of the techniques we discussed for bipartite entanglement, like the PPT criterion and the CCNR criterion, can be extended to multipartite systems.
Okay, but I'm guessing it gets a lot more complicated.
It does. The calculations can become very computationally expensive.
So brute force calculation isn't going to cut it.
Not for large systems.
Okay, so what else can we do?
Well, the thesis reminds us about the Bell inequalities.
The Bell inequalities.
Yes, the same ones that prove the reality of entanglement. Can also be used to probe the structure of multipartite entanglement.
Wait, so they can tell us not just if entanglement is present, but also what kind of entanglement we're dealing with.
Exactly.
Okay, so we can use them to rule out different possibilities.
Yeah, it's like a process of elimination.
I like that.
And then there are entanglement witnesses for multipartite systems as well.
Okay, entanglement witnesses for multipartite systems.
Yeah, they work in a similar way to the bipartite case. But designing them is much more challenging.
So we have these tools for detecting multipartite entanglement. But
Yeah.
once we've found it, what can we actually do with it?
Well, that's the big question.
Yeah.
And it's something that researchers are actively working on.
Okay, so we're still in the early stages here.
Yeah.
But it sounds like multipartite entanglement has a lot of potential.
It does. It has the potential to revolutionize fields like quantum computing, communication, and cryptography.
So this has been quite a journey.
It has.
We started with the historical roots of quantum mechanics, explored the bizarre world of bipartite entanglement, and then ventured into the mind-boggling realm of multipartite entanglement.
It's been a wild ride.
It has.
Yeah.
And we've only scratched the surface. So to all our listeners, if you're feeling inspired, I encourage you to dive deeper into this fascinating field. The quantum world is full of wonders and possibilities.
It is.
And even a glimpse into the strangeness of entanglement can change the way you view reality.
It certainly can.
Well, thank you for joining us on this deep dive into the incredible world of quantum entanglement. We hope you've enjoyed the journey as much as we have. Until next time, keep exploring, keep questioning, and keep wondering about the mysteries of the quantum universe.